In our last video, we have studied speed control of DC shunt motors. In this video, let us study speed control methods used for DC series motors. Speed of DC series motors can be controlled by changing field excitation, that is, by changing flux per pole. So this is flux control method. So there are various ways with which we can control the flux. First is field diverter, second is armature diverter, and third is tapped field control. Now the second way of controlling speed of DC series motor is by changing the resistance in armature circuit. And the third method is by series and parallel control of two or more series motors. We will now discuss these methods in detail. Let us now study first method for flux control, that is field diverter. Now this field diverter is nothing but a small variable resistance which is connected in parallel with the field winding. So this variable resistance connected in parallel with field winding, it is called as field diverter. Now the current in the field diverter, it can be adjusted by changing the resistance of field diverter. Now here total current IA gets divided into two parts. One is ISE and second is I shunt. So therefore, by adjusting the value of field diverter resistance, we can adjust I shunt and remaining current will flow through the field winding. So any desired value of current ISE can be passed through the field winding and desired amount of flux can be produced. So if the resistance of field diverter is reduced, current I shunt will increase and current ISE will decrease. As less current flows through the field winding, flux per pole will also reduce. Now you know that speed is inversely proportional to flux, and therefore with decrease in flux, speed will increase. And therefore, whenever the field diverter resistance is reduced, speed of motor increases. So this is explained here with the help of speed torque curve. Now suppose resistance of field diverter is infinity. So this R shunt is equal to infinite, means this path is open. So I shunt will be equal to 0. So all the current IA will flow through the series field winding. So if this R shunt is infinite, IA and ISE will be equal. So field current will be maximum. Because of that, flux will be maximum and speed will be minimum. So this is the speed torque curve if R shunt is equal to infinity. Now if field diverter resistance R shunt is reduced, then some current I shunt will flow through field diverter and remaining current will flow through the series field winding. Therefore, current in series field winding will reduce, flux will also reduce and speed will increase as represented by this characteristic. If field diverter resistance is further reduced by reducing the value of resistance of this field diverter, then I shunt will again increase, ISE will reduce, flux will reduce and speed will further increase. So this is represented by this red characteristic. Means here R shunt 2, it is less than R shunt 1. So as we go on reducing the resistance of diverter, speed goes on increasing. Now here you have to note one thing, that the value of resistance of this diverter must be very low, because the value of this series field winding resistance RSE, it is also very low. And if you want to divert current through the field diverter, the value of this field diverter, that is R shunt, should be low. Then second important point which is to be noted is this field winding has large inductance, and inductance opposes the change in current through it. Means there is some delay to increase the current in the field winding. And if the field diverter has no inductance, then current through it will increase quickly, whereas current through this field winding will increase slowly, and therefore almost all the current will flow through field diverter. So to avoid this, this field diverter, it must have high inductance, which is comparable with the inductance of this series field winding. Then only the operation will be satisfactory. Let us now see the second method by which flux can be controlled. It is armature diverter method. So in this case, a variable resistance is connected in parallel with armature. That's why it is called as armature diverter. Now current through armature diverter, that is I shunt, it can be adjusted by changing the resistance of armature diverter, and remaining current will flow through armature, that is IA. So here current drawn by motor flows through the series field winding, which is the current ISE, and that current gets divided into two paths. One is I shunt and second is IA. And I shunt and IA can be adjusted by adjusting the resistance of armature diverter. Now suppose load on the motor is constant. So if load on the motor is constant and the armature diverter resistance is reduced, let us see what happens. So if armature diverter resistance is reduced, I shunt will increase, and therefore Ia will decrease. But the load torque is constant. You know that TA is proportional to phi into Ia. So if Ia is reduced and TA is constant, then phi should increase, and therefore motor will draw more current from supply, and therefore if load torque is maintained constant and armature diverter resistance is reduced, then motor will draw more current from supply, and therefore current through field winding, that is ISE, will increase. This will increase flux phi. And as n is inversely proportional to flux, with increase in flux there is decrease in speed, and therefore speed of the motor decreases with increase in flux, that is with reduction in armature diverter resistance. So whenever diverter resistance is reduced, then speed of the motor will also reduce. So here the speed can be controlled by varying the diverter resistance. So here you have to note that with the help of this method, we can obtain only those speeds which are below the normal speed of motor. Because when this diverter resistance is infinite, current through diverter resistance I shunt is equal to 0. Then in that case, the motor will operate at maximum rated speed. Now, if the diverter resistance is reduced, speed of motor will also reduce, and therefore only speeds below normal can be obtained. The third method to control the flux is tapped field control. So here the series field winding has number of taps, and with the help of these taps the number of series field winding turns which are connected in series with armature, these turns can be changed. So with full turns in series, that is with the switch in this first position. So if the switch is in first position, the number of field turns which are connected in series with armature are maximum. So as number of turns of field winding are maximum, then flux will be maximum and speed will be minimum because n is inversely proportional to flux. So therefore, with switch in this first position, the speed will be low. If the switch position is changed, few series field winding turns will be out of this armature circuit, and number of turns in series with armature, these field winding turns will reduce, so flux will reduce and speed will increase, so we will get medium speed. And with switch in the third position, the number of field winding turns which are connected in series with armature will be minimum. So with minimum field turns, flux will be minimum and speed will be maximum, and therefore we will get high speed or maximum speed. So in this case, the speed can be increased in steps by cutting out some of the series field winding turns. So this method is very efficient as compared to previous two methods, because in previous two methods, that is armature diverter and field diverter, there is I square R power loss in the diverter. In this case, as we are not using any resistance in parallel with armature or in parallel with field, there will not be any I square R power loss, and therefore the method is more efficient as compared to the previous method. Let us now study the second method of speed control, that is armature voltage control method. So voltage across armature, it can be changed by changing variable resistance which is connected in series with motor. So in this method, a variable resistance is connected in series with both, that is armature as well as series field winding. Now by changing the value of this resistance, we can change the voltage across armature terminals. So if this resistance is increased, voltage across armature terminals will decrease. And with decrease in armature voltage, speed of the motor decreases. So if the variable resistance connected in series with motor, if it is 0, that is with no resistance, This is the speed torque characteristic, and the motor will operate at its rated speed. Now if the resistance is inserted in series with motor, then the voltage across armature will reduce. And with reduced voltage across armature, the speed torque curve, it will be shifted like this, and the speed of motor will reduce. So with increase in variable resistance connected in series with motor, we can reduce the speed of motor, and therefore with the help of this method we can obtain only those speeds which are below the normal speed of motor. So this method is suitable for obtaining only speeds below normal. The major disadvantage of this method is large current is flowing through this resistance, and therefore large amount of power, that is because of I square R loss, will be wasted in the form of heat in this controlling resistance, and therefore efficiency will be very low. This is the main drawback of armature voltage control method. Now we have studied two methods for speed control: armature voltage control and flux control. Let us see what are the relative merits and demerits of these first two methods. So first of all, armature voltage control. So as already seen, large amount of power is wasted in the controller resistance in case of armature voltage control, and therefore efficiency will be very low. Then because of large I square R power loss in controller resistance, it is get heated, and therefore we need expensive arrangement for dissipation of heat which is produced in the controller resistance, and therefore the method is not economical also. So armature voltage control is less efficient and less economical, and with the help of armature voltage control we can obtain only speeds below normal, and therefore this armature voltage control method is very rarely used. It can be used when low speeds are required for a short duration only because of its low efficiency and high cost. Then the second method is field control. So in this case, the I square R power loss in the diverter is comparatively less, and therefore the method is more efficient and economical. But in this case, we can obtain speeds only above normal speed of motor. Then one major disadvantage of field control is when the flux becomes weak, then the commutation becomes unsatisfactory, and therefore there is excessive sparking at the brushes if the flux becomes very weak. And if we want speeds both above or below normal, then both the speeds can be obtained by combining the two methods, that is armature voltage control method for speeds below normal and field control method for speeds above normal. The third method for speed control of DC series motors is series parallel control of motors. So this method is widely used in electric traction, that is in electric locomotives or trains, where two or more such motors are mechanically coupled and then these motors are either connected in series or in parallel. So when the speed is low, then the motors are connected in series, whereas for high speeds, the motors are connected in parallel. Let us now see torque and speed in case of series and parallel connections. So when the two motors are connected in series, current in each motor will be same and it is equal to I, whereas voltage across each motor will be equal to V divided by 2. Now the speed of motor N, it is proportional to EB upon phi, and this back EMF EB is proportional to applied voltage and phi is proportional to field current. So in this case, applied voltage is V by 2 and field current is I. And therefore, N is proportional to V by 2 upon I, which is equal to V upon 2I. So in this case, N is proportional to V divided by 2I. Now the torque is proportional to the product of flux and armature current. That is, T is proportional to phi into I. And as the motor is series motor, phi is also proportional to I. And therefore, T is proportional to I into I because current flowing through each motor is I. And therefore, T is proportional to I square. Now if we consider parallel connection, then current in each motor will be I by 2, whereas the voltage across both the motors is equal to V. And therefore, as N is proportional to applied voltage divided by field current, here applied voltage is V and field current is I by 2. And therefore, N is proportional to V upon I by 2, which is equal to 2V divided by I. And as torque is proportional to phi into I and phi is again proportional to I and I is equal to I by 2, T is proportional to I by 2 into I by 2, which is proportional to I square by 4. So if you compare speed and torque in series and parallel connection, we can see that in case of series connection, speed is less and it is 4 times less as compared to parallel connection. Whereas in case of series connection, torque is more and it is 4 times more as compared to torque in parallel connection. And therefore, we can control the speed by connecting the motors in series and in parallel. So the speed in case of series connection is 1/4 of the speed in parallel connection, and the torque in case of series connection is 4 times the torque in parallel connection. Thank you. In our next video, we will solve few numerical problems on speed control of DC series motors.